Welcome back. You ever wonder how we measure something that's completely invisible, but also potentially pretty dangerous, like radiation? Well, today, we're going to crack open the secret of how certain crystals can literally remember being exposed to it. So let's dive into the pretty amazing world of thermoluminescent dosimetry. Okay, here's the game plan. First up, we'll talk about the problem itself, this invisible danger. Then we'll get into the cool science behind the crystal's memory. After that, we'll see how we actually read that memory, understand why it's so important for keeping people safe, and finally look at its legacy and what makes it so special. So right off the bat, we're facing a really fundamental challenge. Ionizing radiation is this powerful force that's all around us, from medical x-rays to cosmic rays zipping through space. But it gives us this one huge problem.
Exactly. Think about it. You can't see it, you can't feel it, you can't hear it. So how can the people who work around it every single day possibly know if they're safe? How on earth do you put a number on a threat that's totally invisible?
Well, the answer is just so elegant, it almost sounds like science fiction. You don't measure the radiation directly. You trap its energy. You give it something to leave a footprint on, a tiny, brilliantly designed crystal that basically acts as a witness.
And this brings us right to the heart of the science. This isn't magic. It's pure physics. Let's pull back the curtain and see exactly how these materials can hold on to a record of radiation exposure, essentially giving the crystal a memory. The whole principle is called thermoluminescence. And really, the name itself is a huge clue if you break it down. You've got thermo, which means heat, and luminescence, which means emitting light. So you got it, it's light from heat. So here's how it works. I want you to think of the crystal like a tiny rechargeable light battery. Normally, in its stable state, all its electrons are just chilling out. But when radiation zips through, it acts like a bowling ball, knocking some of those electrons into these special traps in the crystal's structure. And they get stuck there, holding onto that energy. The more radiation that passes through, well, the more electrons get trapped. Now, of course, not just any old crystal will do the trick. The magic really comes from these specific materials called phosphors. Things like lithium fluoride are just perfect because their atomic structure has just the right kind of tiny imperfections to create those electron traps we were just talking about. They are incredibly good and incredibly reliable at storing this energy. Okay, so the crystal has stored the energy, it has a memory of the radiation dose locked inside. But how do we read that memory? How do we actually get that information back out so it's useful?
All right, so here's how it goes down. The little crystal disc from the badge is placed into a special reader. Then the reader heats the crystal up in a very, very controlled way. That heat gives those trapped electrons just enough of a kick to escape and jump back to their normal state. And boom. As they do that, they release all that stored energy as a tiny flash of light. A super-sensitive detector measures exactly how bright that light is, because the brightness tells you everything. It's directly proportional to the original radiation dose.
And this is what you get at the end of the day. A number, a concrete, precise measurement of exposure. Something like 0.05 millisieverts. It's what turns that invisible threat into actual, manageable data. This lets safety officers track every bit of exposure and make sure everyone stays well below safe limits. But these badges are even cleverer than that. See, they don't just have one crystal. A typical badge has a whole team of them, and each one is sitting behind a different filter. So you'll have an open window that lets everything in. Then maybe a plastic filter that blocks the weaker beta particles. Then you've got different metal filters that help tell the difference between low and high energy gamma rays. It's brilliant because it lets scientists figure out not just how much radiation someone was exposed to, but what kind it was, too. Now, this technology isn't just some cool experiment stuck in a lab. It is a critical, life-saving tool that protects people in high-stakes jobs every single day. This is where the science meets the real world. So who actually wears the badge? Well, the list is long. Think about radiologists and X-ray techs in hospitals, workers in nuclear power plants, researchers, even astronauts way up in space measuring cosmic rays. They're also used to double-check that patients getting cancer therapy are receiving the exact perfect dose of radiation. From hospitals to space stations, these little badges are true silent guardians. This quote just nails it, doesn't it? It sums the whole thing up. Radiation is part of our universe. The danger doesn't come from it just existing. It comes from us not being able to see it, to measure it, to quantify it. Technology like the TLD completely removes that blindness. So,
To really appreciate how great this technology is, let's put it into context and see why it became such a cornerstone of radiation safety.
So before TLDs, the gold standard was something called a film badge, which worked kind of like old camera film. But as you can see here, TLDs were a massive, massive leap forward. The biggest game changer? They're usable. That heating process that reads the dose, it also resets the crystal. It wipes the slate clean, making it ready to go again. Plus, they're way more sensitive and a lot tougher. They aren't really affected by heat or humidity, which means you get more accurate, more reliable readings every time.
So if you remember just one thing, let it be this. TLDs are a masterpiece of simple, elegant engineering. They don't need batteries. They don't have any wires. They're completely passive. They just sit there, silently and reliably recording what's happening, acting as our eyes on a totally invisible force.
And, that leaves us with a pretty fascinating thought. If we can design a crystal that literally remembers radiation, what else is possible? What other invisible forces or pollutants or energies could we one day measure just by creating the right smart material to witness them for us? The potential is, well, it's truly glowing. Thanks for tuning in.